Hi, and welcome to another physics class. In today's lesson, we're going to talk about waves. Now, most of you might be thinking about water waves or sound waves, and those are correct. Sometimes you may have seen waves at the stadium with fans, and that's another type of wave. But the reality is waves are all around us. Sometimes we see them, sometimes we don't. So the question of how are you seeing this video, for example, is through light waves. You're hearing me through sound waves. And whatever device you're using, chances are you're probably using Wi-Fi or mobile data in order to receive the packets, in order to be able to watch this video. That's from radio waves. Now, a wave is a rhythmic disturbance or vibration, or sometimes referred to an oscillation that carries energy through matter or space. That's the important part, is that waves transfer energy, not matter or mass. Waves are created by vibrations, and a single wave pulse is going to be a single impulse. There's two types of waves. There's a mechanical wave and an electromagnetic wave. A mechanical wave is one that travels as an oscillation through a medium, meaning that it has to have a medium. It can't travel through a vacuum. Examples of this include water waves and sound waves. In an electromagnetic wave, it's a wave that consists of electric and magnetic fields, and they don't require a medium. The energy can travel through space. And examples of these include light and radio waves. When we talk about mechanical waves, there's two types of mechanical waves. The first one is going to be a transverse wave, in which particles move perpendicular to the direction in which the wave moves, and these look like sine curves. Some of these examples include radio, microwaves, infrared, and even the SMU Sculpture. Now you can go ahead and watch a video of this, but the SMU Sculpture actually moves up and down and as it progresses through. Some examples of transverse waves are going to be wave energy moves left to right and the oscillation is up and down. Remember, this is the one that moves perpendicular to the movement of the wave. So the energy goes from left to right and the oscillations are up and down. These examples include what the fans do in the wave, water waves, and the SMU Sculpture. So here we see some transverse waves that are in motion, and this is what we mean by the wave movement is from left to right, but the oscillation is up and down. Moving on to the parts of a transverse wave, this is very important. So the crest is going to be the top of the wave or the highest point above the equilibrium or the resting position. The bottom of it is going to be the trough, and the lowest point below the equilibrium or the resting position. The wavelength with the symbol of lambda, the inverse like in y, is a distance between two successive or adjacent similar parts of a wave. And that's the correct definition of the wavelength. It is the length to complete one wave. Now, as we look in the picture below, there are several different ways you can go ahead and identify wavelengths. Sometimes you can count it from a crest to crest, because from the beginning of that first crest to the beginning of that second crest, that is the same adjacent part. You can also do it from the bottom with the trough. We've got the wavelength from that bottom portion to the next one, and that would also be considered the wavelength. The wavelength, again, is the distance between two successive parts that are adjacent or similar to each other. So we see our final and third wavelength there, or third example of the wavelength, and it is from the start of where you see the node to the other one. Now, speaking of nodes, I have not labeled every single one possible of all these. Every similar point is going to have the same names, but for the sake of keeping it organized, not everything is labeled. So the nodes are each one of those positions that it crosses the equilibrium. The antinodes are the top and the bottom points of at any time. And at the very top, we would consider that the crest, and at the very bottom, we would consider the troughs. And the amplitude could be from the distance from the point of maximum amplitude, which is the halfway down or the halfway up, meaning from equilibrium all the way down, or from the equilibrium all the way up. And the amplitude is a distance from normal resting position to the top of the crest or the bottom of the trough. Going back to wavelength, the best way to identify how many wavelengths there are, is to consider one hill and one hole. So if we start at the origin and we look at that, we could consider that as one hill. Followed when it crosses the equilibrium and it goes through in the bottom portion and all the way to the end of where you see that first mention of the node with the purple, that would be considered the hole. So one hill and one hole gives us one wavelength. So in this wave, we actually have two wavelengths. There's a second type of a mechanical wave, and that's the longitudinal waves. In this case, particles move parallel to the direction which the wave moves, and these are also known as compression waves. Some examples of longitudinal waves are sound, some earthquakes, and tsunamis in the ocean. Now with compression waves, we're going to see different examples, and we're going to break it down to each part. Again, they oscillate in the same or parallel direction as the wave movement. The wave energy moves from left to right, so the oscillation is also left to right. And some examples of these are going to be springs, sound waves, seismic waves, and like a slinky going from side to side. All right, and here are some animations of the longitudinal waves moving from side to side, and the oscillations are also side to side. Now looking at the parts of longitudinal waves, the compression is where they are compressed. So you see an increase in medium density. Think of a slinky that has very tight coils, and then you have a rarefaction. Think of the slinky that is now stretched out. So the compression is where you have an increase in medium density, and the rarefaction is a decrease in that medium density. You could think of the word rare as it happens infrequently. So the rarefaction is where you have very few lines in between, whereas the compression is where they're all compressed tightly together. Then the wavelength, again, is going to be distance between successive parts of the wave. So in this case, it would have to be from the compression to the compression, or from the rarefaction to the rarefaction. Here are some more images to see the differences between them. And the compressions, as you can see, are the more dense ones, and the rarefactions are the scattered ones. And at the bottom, we'll see examples of wavelengths. So you can go from a rarefaction to a rarefaction, and that would be considered a wavelength. And you could also go from a compression to a compression, and that could be a wavelength. So here we can compare the longitudinal waves versus the transverse waves. You'll notice that they have some of the same parts labeled. However, overall, they look very different. And at the bottom picture, letter A, that is a longitudinal wave. And letter B, that is a transverse wave. Frequency and period. Now, we've talked about frequency and period both before, and we're going to get back into it for waves. But starting with wavelength, it is a distance to complete one full cycle. The symbol for wavelength is that upside down Y, and it's called lambda, with the units being in meters because you're dealing with lengths. Frequency is the number of cycles or oscillations per second. The symbol is going to be, or the variable is going to be a lowercase f with the units of hertz. Another alternative units is also the wave number of wavelengths per second. The frequency of a wave is determined by the period of the wave, and period, if you remember from last time or previously, is at the time that it takes to complete one cycle. Now, the variable for period is a capital T, not a lowercase t, because lowercase t is time. And the units for period is in seconds. So in equation 42, we see for our equations for frequency and for period as well, and they are inverses of each other. Moving on to problems, we've got a red color's frequency is 10 to the 15 hertz. What's the period of the red light? Now, these problems are fairly simple, so I'm not going to go ahead and explain the math because you can see the steps. But as long as you go ahead and label everything, then you can go ahead and figure out which equation to use. For speed of the wave is the distance the wave moves over time. It's determined by the medium through which the wave moves. And these examples of these mediums include solid, liquid, and gas. And our equation is going to be equation number 43, where velocity is equal to frequency times the wavelength. Here's another problem, fairly simple. We've got a frequency of 5 hertz and the speed of the wave is 15 meters per second. And we're solving for wavelength. Pretty straightforward once you label everything. And finally, moving on to our last problem. In this case, there's one thing I'd like to point out, and it says the wave with a frequency of 20 hertz travels along a slinky. So we know what our frequency is. The question is asking for what is the speed of the wave, so we're looking for velocity. However, it doesn't directly mention wavelength. It says that if the distance between successive compressions is 0.4 meters. If you remember, the definition of wavelength is a distance between two successive points or adjacent points of a wave. So the distance between two successive compressions would fit the bill for the wavelength. So our wavelength is actually 0.4 meters. And moving on, we've got standing waves. Standing waves are waves that appear to be standing still, caused by the constructive and destructive interference of two waves that are similar in frequency. So they occur when two opposite waves combine to result in a standing wave, and this is the result of either constructive and destructive interference. And we'll see examples of those in the upcoming slides. And they occur when the amplitude and the frequency are identical. So here's a time-lapse view of a standing wave. Each one is a different second, if you will. And as it goes, and eventually you see number 8, it's the complete scenario that we would see with our own eyes, and it will look as if the wave is standing still. Now, destructive interference, also called cancellation, is when the crest of one wave and the trough of another wave arrive out at a phase particular movement in time, producing a smaller resultant wave. Sometimes they could even completely cancel out if they're the same amount. For example, we see before the interference that the hill and the hole are about the same size, and during the interference, when they combine, that new green line has been canceled out. So that's where it would have been. It would be perfectly flat there. With constructive interference is when two crests, or two troughs, depending on which way you're going, arrive in a phase at a particular moment in time and produce a bigger resultant wave. So in this case, we've got two crests headed towards each other. They're two hills, if you will. They add up and they make a much bigger hill. And finally, last example of standing waves. If you would look at these parts, we've got antinodes and nodes. So the node is the point where the combined wave doesn't move, and the antinode is the point where the displacement is the greatest, or would be considered the bump. All right, that concludes today's lesson. Hope you found this video helpful. Thank you and have a great day.